Assalamu alaikum. My name is Zoha Naim, roll number 21TE01 from Telecommunication Engineering Department, UAT TAXILA. Today I will be discussing lab number 5 of digital signal processing. In the task 1, we are required to create my DFT function and my IDFT function. My DFT function calculates the discrete Fourier transform of an input sequence X. It iterates over each frequency index K and each sample index N. It computes the DFT sum according to the DFT formula and stores the result in the array X. My IDFT function calculates inverse discrete Fourier transform of an input array of the DFT coefficients. Similar to my DFT function, it iterates over each sample index n and each frequency index k, computes the IDFT sum according to the IDFT formula, and stores the result in the array x. Finally, it normalizes the reconstructed signal by dividing each sample by n. These functions implement the mathematical formulas for DFT and IDFT, allowing us to compute the frequency domain representation of a signal and reconstruct the original signal from its frequency components. Here is the example usage of the previously constructed functions. The provided code computes the DFT of the input signals x1, x2, and x3 using my DFT function, then reconstructs the original signals using the IDFT function. Finally, it displays both the original and reconstructed signals for each sequence. This code calculates the DFT of each input sequence using my DFT function. After obtaining the DFT coefficients x, the code uses my IDFT function to reconstruct the original signals. Similar to DFT computation, this function iterates over each sample index and each frequency index, computes the IDFT sum according to the formula, and stores the result. The code displays the original and reconstructed signals for each input sequence using MATLAB's display function. The output will show the original sequences followed by their reconstructions. If the reconstructions are accurate, the displayed results should be close to the original ones. Moving on to task 2. The code defines several input signals x1, x2 up to x11. Each signal represents a sequence of numbers. The FFT function is used to compute the discrete time Fourier transform of each input signal. It calculates the DFT coefficients representing the signal in frequency domain. For each input signal, the DFT is computed and stored in the variables x1, x2 up to x11. The length of each input signal is stored in variables n1, n2 up to n11. This represents the number of samples in each signal. A figure with subplots is created to display the magnitude spectra of each signal. For each subplot, the stem function is used to plot the magnitude spectrum of the corresponding DFT coefficients. Absolute function is applied to compute the magnitude of each complex DFT array. The title function is used to set the title of each subplot, indicating the signal name and its length. The figure with subplots shows the magnitude spectra of each signal. Each subplot shows the magnitude spectrum of a signal with x-axis representing the frequency and y-axis representing the magnitude. The key observations made from this code are: as the length of the signals increases by adding the trailing zeros, the frequency resolution improves. Longer signals with more zeros provide a finer frequency resolution, allowing for the better separation of frequency components in the spectrum. This code helps visualize how the frequency resolution changes with the length of signals, which is an important aspect when analyzing signals in the frequency domain. For task 3, input signal is given. The X defines an arbitrary input signal consisting of 4 samples. FFT function is used to calculate the discrete time Fourier transform of the function. The real and imaginary parts are extracted, the phase and magnitudes are also extracted, and the results are displayed. Moving on to task 4. Several input signals are defined, each representing a sequence of numbers with varying lengths and zero padding. The FFT function is used to calculate the discrete time Fourier transform of each input signal. DFTs for each signal are stored in the variables x1, x2 up to x11. The length of each input signal is stored in variable n1, n2 up to n11 representing the number of samples in each signal. For each signal, a frequency axis f1, f2 up to f11 is created. The magnitude spectrum of each signal is plotted using the stem function. Each subplot displays the magnitude of DFT coefficients against the corresponding frequency. The title of each subplot indicates the signal name and its length. Similarly to the magnitude spectrum, the phase spectrum of each signal is also plotted. Each subplot shows the phase angle of the DFT coefficients against frequency. The power spectrum of each signal is also plotted. Each subplot displays the square of the magnitude of DFT coefficients against frequency, representing the power of frequency components. Here we can see the magnitude plotting. Here's the phase spectrum, and now the power spectrum. Okay, for here are the magnitude spectrums. Here we have phase spectrums, and now for the power spectrums. The key observations that we get from this code are: zero padding increases the frequency resolution of DFT, allowing for the better separation of frequency components in the spectrum. Magnitude spectrum shows the amplitude of each frequency component. Phase spectrum shows the phase angle of each frequency component. Power spectrum shows the power square of magnitude of each frequency component. This code provides a comprehensive analysis of the frequency component of each input signal, including magnitude, phase, and power information using the discrete time Fourier transform. Thank you so much for watching.